Okay, so here's a March 27th follow-up. First thing we want to talk about is nucleophilic aromatic substitution. Mainly the reversibility of it, as well as this question about what does this mean by late transition states. Okay, so nucleophilic aromatic substitution. What's occurring in a nucleophilic aromatic substitution? In fact, let's just use pyridine as an example. Is you have an electron deficient ring, either a nitro group in the ortho or para position, or you have an idea of this pyridine, this moiety right here. We add the electrons go up. And these electrons right here can swing down, and they can kick off either a Cl- or an OMe. What makes this first step difficult is you're going from a strong base to an even stronger base. Now, what makes this possible is that this carbanion is resonance stabilized, but even that is not favorable. It needs to be rather strongly resonance stabilized. So it needs to really stabilize that negative charge. And in the case of pyridine type species, that negative charge is stabilized by putting the electron density up onto the nitrogen. Making this the major resonance structure. And then the electrons come back down and kick off chlorine. Now, this last step really is irreversible. I think on some of the answer keys I showed it as reversible, but it really, that chloride is very, very unlikely to add back, because it's a step for the methoxy to add into there. That's a strong base. Chloride itself isn't a strong base. That makes it infinitely harder for that to add to it. So the backwards arrow here is so small, it might as well be undetectable. So really that last step is definitely irreversible. If we were to plot out the energy of this, we start off with a molecule that's a strong base, that's methoxide, and an aromatic molecule. And then we're breaking the resonance, so that's a pretty steep energy curve. That gets to, and then you get, it relaxes to form the resulting carbanion. That's resonance stabilized. And then afterwards, it's child's play for this carbanion to kick out the chloride, so there's not much of a barrier at all. And since we're starting out with a strong base, and we're ending with a weak base, this is a pretty exothermic reaction. And so together, the starting materials are less energetic than the product, so you down. Okay. The rate of the reaction is determined by the height of this barrier right here. This transition state is very difficult to model And so we turn to something called Hammond's postulate. And Hammond's postulate states that late transition states are more product-like and early transition states are more starting material-like. Well, this idea of early transition states and late transition states essentially is just, is this transition state closer into energy to the starting materials, or is it closer in energy to the products? In this case, the product being this intermediate right here. So what a late transition state means is it's closer in energy to the intermediate / products. An early transition state means it's closer in energy to the starting material. So an example of an early transition state would look something like that. So an example of a late transition state looks like this. So that's awfully confusing. What I want you to remember is in the cases of these reactions right here, where it requires a huge amount of energy to get them started. So breaking aromaticity is an example of that. What that means is that the transition states can be heavily influenced by what the intermediate looks like. The lower in energy this intermediate is, the more stable this intermediate is. The lower in energy this transition state's going to be. And the lower in energy that transition state's going to be, the faster the reaction is going to occur. And that's what I mean by that. Okay. And then there was also a question on Piazza about how to recognize unstable molecules. Specifically, this was a question dealing with problem set 19, 1J. And this was the reaction that was a student answer in an exam a while ago. I know that this is so tempting to see when you have a carbonyl, think oxidize it from an alcohol. No. Ketones and aldehydes come from alcohols. This is a very common mistake. Carboxylic acids can come from alcohols. But esters and amides, they come from different reactions. Not by oxidation. And that's because this motif is an unstable motif. Whenever you see an OH attached to an sp3 carbon, this will be unstable if non-carbons / non-hydrogens are also attached with limited examples to the contrary. What do I mean by that? If you have a molecule like this, this is a hemiaminal. This, no, I don't even know what the name of this is. A chlorohydrin or something like that. This and this. This is a hydrate. This is a hemiacetal. All of these are unstable molecules. The hemiaminal will either become an aminium or become a carbonyl. One of those two things. Point is, it is not stable enough to use in a synthesis. These are mechanistic intermediates. The only examples of hemiacetals or hemiaminals that are actually stable enough to be used in synthesis reactions are things that are cyclic, preferably things that form 5 or 6 membered rings. These are stable, but they are the exception to the rule. If you ever draw an OH and that's attached to an sp3 carbon, and there's something else that's not a carbon or hydrogen attached to that sp3 carbon, chances are that molecule is going to be unstable and you can't put it in a bottle. If you can't put it in a bottle, then you can't use it in a synthesis problem. It's not a valid starting material. So watch out for these. Okay, benzyl chloride. How do you know if that's going to do an SN1 reaction or an SN2 reaction? Well, benzyl chloride can do either one, mainly because it's primary, unhindered, so that seems to favor SN2. But if that chlorine were to leave, you can form a resonance stabilized carbocation. So that seems to imply SN1. So how do you know if you're looking at an SN1 or an SN2? Well, it really depends on your nucleophile. If your nucleophile is a good nucleophile, then you're looking at more of an SN2. Especially the more basic the nucleophile, the more likely it is for an SN2. Because carbocations are strong acids, and you really shouldn't have strong acids and strong bases together. The cyanide is a moderate base, conjugate pKa, roughly around 10. That's going to be SN2. Hydroxide, conjugate pKa, around 15. That's going to be SN2. Water, that is a weak nucleophile. Its conjugate pKa is around 0 or so. That's going to be SN1. Neutral oxygens have a tendency to do SN1 reactions. Anions, basic molecules, have a tendency to do SN2 reactions. Now we see carbocations used in Friedel-Crafts reactions. And other EAS reactions. Because these are strong electrophiles. You need strong electrophiles because aromatic rings are poor nucleophiles. So, since aromatic rings are poor nucleophiles, if you use an aromatic ring as a nucleophile, do not do SN2 except under very limited circumstances, like methyl carbocations are really bad to form. Use S, and it should be very specific, do not do SN2 mechanisms. Aromatic rings, to break the aromaticity, you need a really good electrophile. Really good electrophile means a carbocation. And a carbocation means SN1, not SN2.